Today I'd like to go over protons and neutrons a little bit, and what protons and neutrons are composed of, and what does color have to do with that anyway. Let's start out with a little bit about color. If we mix colors of light together, it's called color addition, or these are additive colors. It's not like mixing ink or paint. Wavelengths of light combine and we get interference going on. We get constructive interference in certain cases and destructive interference. In the case of red, green, and blue light mixing together, we get total addition of colors. They all three add up to form white light. Okay, that's a mix of all three of the primary colors, red, green, and blue. If we just mix green and blue together, those colors of light will form a wavelength, and it'll form wavelengths that are intermediate between the wavelengths of green and blue light on the visible light spectrum. And that's called cyan. It's kind of a light blue color. If we mix blue light with red light, we're going to get an intermediate wavelength called magenta. I didn't do a very good job of coloring that in. It's kind of a light violet type color. If we mix red light with green light, the place on the electromagnetic spectrum that's intermediate between that would be yellow, and so we'd see yellow light. But if we mix all three, red, green, and blue, we get white light. Okay, again, this is not to be confused with ink. Ink is a subtractive process. If you take yellow ink and mix it with cyan ink and mix it with magenta ink, you're going to get black. And that's why with your printer ink, it usually comes in some little cartridges. You usually have a yellow cartridge, a cyan cartridge, and a magenta cartridge. And those three colors together would form black. Those would be subtractive colors when you deal with mixing of pigments. But when you're mixing light, it's additive. Okay, now we're just going to take a little journey away from that and take a look at, let's say, an atom. Let's say this is an electron cloud surrounding the nucleus of the atom. There's a nucleus. And the nucleus is made up of a certain number of positively charged protons and neutrons which have no electric charge. Now this, of course, is not to scale. This is a cartoon view of an atom. An actual atom, say of hydrogen, if we were to draw it to scale, let's say the nucleus was the size of a bowling ball, the electron cloud around the bowling ball would be 20 miles in diameter. That would be more of a correct scale there. So really, I wouldn't be able to draw you wouldn't be able to see the nucleus if I drew the electron cloud this big. It would be a tiny, tiny, tiny point that you wouldn't be able to see on there. Now, if we take and zoom in on one of those protons in there, inside the nucleus, a proton has an electric charge of +1 electric charge, which is equal in magnitude but opposite in sign from that of an electron. Okay, so I'll draw a proton. So now this circle represents a proton that I've zoomed in on. Okay, guess what? Inside that proton, it's made up of three smaller particles called quarks. Quarks. So that's your new word for the day. Quarks it's just an invented word, and these quarks have been known to exist since the early 60s. Now, in the proton, it contains three quarks, and the quarks have come in different flavors. There are actually 6 flavors that quarks come in. And these flavors are really, they determine the electric charge charge flavors, right? So we have the 6 flavors being up, symbolized by the letter U, and then down, symbolized by the letter D. We have charm, C, versus strange, S, and then that's 4 of them. The 5th one would be top, T, and then bottom, B. Okay, so those are the 6 flavors. Now it turns out that in a proton, we have only 2 of those flavors occurring, the flavored quarks occurring in there. We have 2 up quarks and a down quark. Now, different flavors have different electric charges. The up quarks have a charge of plus 2/3, so there's one for that up quark. Here's another one for this up quark. And then a down quark happens to have a charge of negative 1/3. If I add those 3 charges up, we have 2/3 and 2/3 is 4/3 minus 1/3. We get a positive 3/3, which is equal to plus 1. And so that's why a proton has a charge of plus 1. It's because of those up and down quarks that make up the proton. Okay. Now, if we zoom in on a neutron, we'll zoom in on a neutron. So here's a neutron now. By the way, a neutron is slightly more massive than a proton, and even though a lot of times you think of protons and neutrons being of the same mass and so forth, neutrons are slightly heavier, but we'll get to that some other time. A neutron, as I said before, has 0 electric charge, and that has to do with the kind of quark flavors. Okay, the neutron happens to have 2 downs and an up. I like to rearrange it and just write it out as dud. Okay, remember a down quark has a negative 1/3 charge, so we have 1 there. An up has a positive 2/3 charge, flavor, and another down has a negative 1/3 charge. If I add those together, that comes out to be 0. 0 electric charge, just because of the charge flavors that make up a neutron. Okay, so that may be something new to you. Now, besides having 6 flavors that deal with electric charges, quarks also come in various colors. And the colors is, of course, just an analogy, right? They're not really red, blue, and green, but scientists think of them in those terms. These colors indicate the amount of strong force that, or strong charge, you might say, that is in the nucleus. Because without a strong force, the nucleus would fly apart, right? All those positive charged protons that are inside that nucleus there, they would repel away from each other because of electrical repulsion. Like charges repel, right? So they'd fly apart. But there's something called a strong force at this small microscopic scale, brought to you by the colors of quarks, that helps prevent those protons from flying apart. So each neutron, each proton actually provides some strong force into that nucleus, so it helps hold it together. So let's look at the different quark colors, we might say, that quarks have, possible colors. Okay, we could just have, let's say, blue, red, green. Now, they're not really those colors, are they? But it's, like I said, it's just an analogy. If blue, red, and green quarks happen to occur in the same particle, then they they happen to exist in that particle happens to exist in nature. Blue, red, and green light mix together to form white light. Blue, red, and green quarks mix together to form a particle that actually can exist. So this particle can exist on its own in nature if we have a mix of quark colors that form white. So in this case, if we have the first quark having a blue color, blue in quotes, and another quark in that same proton, let's say, that happens to be red in color, and then another one that would have a quark color of green, they mix real well together to form white, or what's reminiscent to a scientist as white, and that tells the scientist this particle can really exist by itself in nature. Another possibility would be if we take cyan, yellow, and magenta. If an antiquark, let's say, is cyan, okay, and we have another antiquark which would be, let's say, yellow, and another antiquark, let's say, which would be magenta. Those three also, if we look at the colors, would mix together to form white light. And in the same line of thinking, inside a subatomic particle, if you have these three quarks with those color combinations, this particle can exist in nature. Okay? Now, if you have a particle made up of three quarks like this that are existing in nature, these are called baryons. So a baryon is a particle composed of three quarks composed of three quarks. And of course, if it's a particle that's existing in nature, those three quarks happen to have colors whose mix ends up reminding scientists of white in color. Okay, so that's what a baryon is. So I know it's a little trivia word. Okay, so in summary then, what does color have to do with protons and neutrons? The color charges are really an indication of strong force that's holding that nucleus together. It's holding those protons, preventing those protons from pushing away from each other. The only kinds of particles that can exist in nature are ones where the color charges mix together to form white. If you have a particle made up of three quarks like this, that's called a baryon. Okay? Thanks a lot, everybody.